Okay, welcome back to part 2 of lecture 7. So here we're going to continue with our basic differentiation rules. And let's talk next about the exponential function. So here's a theorem, and we'll prove this one, although I think it'll be kind of a slog for some of us, but let's take a look at it. So the derivative with respect to x of e to the x is e to the x. Okay, so one of the most intriguing characteristics of the natural exponential function is that it is, as it says here, its own derivative. Okay, so what that means is that the slope, if given the function f of x equals e to the x, f prime of x is equal to e to the x as well. That means is that the derivative is identical to the function itself. So the slope of e to the x is always going to be the y component of any ordered pair that lies on the graph of the function e to the x. So that's kind of remarkable. And let's jump into the proof and see if we can figure out why this might be the case. Okay, so let's go ahead and try to prove this. So again, we'll start with the definition. So f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Okay, now what we got to do is for these f's up here, we got to plug in the function e to the x. So we get e to the x plus delta x minus e to the x. And then that's all divided by delta x. All right, and for people who are comfortable with these exponents, you'll see right away, of course, that, oh, I'm sorry, I should have put the limit in there. Okay, don't forget that's important. So this is the limit as delta x goes to 0. And we can break this apart into e to the x times e to the delta x, and then minus e to the x. Okay, and that's all divided by delta x. All right, and then of course we can do some factoring. Like so, right? Not a problem. Okay. Now here's where we have to get a little tricky. Okay, so the definition, so for people who've been very thorough with their algebra upbringing, one of the things you'll know is that, this is kind of a side note here. Okay, e, the constant, is equal to the limit as n goes to infinity of the following: 1 plus 1 over n to the nth power. Okay, so this is the limiting process from which e is derived. Okay, now we're going to use this inside of this expression up here. And so one of the things you can do here is you'll want to say, let's let n equal 1 over delta x. Okay, and then so of course that implies that delta x is 1 over n, right? So those two things are true. So let's use this notation, this delta x stuff, and plug it into this expression and see what we get. Well, what you'll see is that e equals the limit as n goes to infinity. Well, if n is 1 over delta x, then that's the same thing as saying e is the limit as delta x goes to 0, right? And then inside here, instead of 1 plus 1 over n, 1 over n is delta x, we're going to put delta x here. And then instead of n, we're going to put 1 over delta x. Okay, all right, so you'll notice here that we're inching towards something we can use up top here. Okay, so this is kind of a side note. All right, so this would be the piece that you probably, well, maybe are not familiar with. This piece is not common knowledge to your Calc 1 students. So dig into this a little more. But we're going to use this fact. You're going to have to trust me on it for now. You can go verify this easily. But trust me on this for now. We're going to use this, and then we're just going to do some variable substitution here to get it into an expression that involves delta x instead. Okay. All right. So what does this mean? So, well, when delta x is sufficiently small, what this implies is that e is approximately 1 plus delta x over 1 to the 1 over delta x, right? Right, so for small values of delta x, this is roughly true, right? Okay, and this is going to imply then, we can exponentiate both sides by delta x. This is going to imply that e to the delta x is approximately equal to 1 plus delta x. Okay, and we can use, so this here appears in our expression up above, and we're going to take this and we're going to substitute it in. We're going to put this piece in instead. Okay, so let me just put a little asterisk because we're going to move this argument down to the next level here. And so we're going to say that that prior expression is equal to the limit as delta x goes to 0 of e to the x. Okay, now instead of e to the delta x, we're going to plug in 1 plus delta x. Okay, so it'll be 1 plus delta x minus 1. And then the whole thing divided by delta x. Okay, so that's good. Looking good so far. All right, and we can just distribute the e to the x here. We can expand this numerator and do some cancellations. So let's do that. The limit as delta x goes to 0. And so you'd get e to the x plus delta x e to the x, right? And then multiply the e to the x by the end, so minus e to the x. And then the whole thing divided by delta x. Okay. And, of course, e to the x and minus e to the x, of course, you just combine those, you'd get nothing. You'd get a 0. So this is all the limit as delta x goes to 0 of e to the x times delta x all over delta x. And of course, we're going to cancel the delta x's, and we'll see that the result follows directly. Okay, and then of course, taking that limit, the delta x isn't even a term in the expression, so it's just e to the x. Okay, now the tricky part of this argument kind of comes from right here. Right, understanding that piece of it, and then once you understand this piece of it, recognizing that in the limit, e to the delta x is equal to 1 plus delta x and can be substituted. Knowing that we're going to be taking the limit, we know that these two are going to be equivalent. Okay, so that piece of it is fine, right? As delta x goes to 0, this goes to 0, that goes to 0, they both equal 1, right? So that's obvious, right? Hopefully. All right, so the fact that we can substitute this in is only really true in the case of taking the limit as delta x goes to 0. Okay, so keep that in mind. But then everything else is just basically algebra. All right, so that's an interesting proof. It's an interesting theorem. So the theorem can be it can be interpreted graphically, right? We can think of this. So let me try to draw a reasonable natural exponential function. It kind of comes through, we'll say this is the point 0, 1. Okay, the graph kind of hugs the x-axis, comes through there, and then sort of shoots off, right? So what this means then is that for each of these, tangent lines at any one of these points, the slope there is going to be like 1, comma e here, right? 0, comma 1 right there, right? So this would be the point x equals 1, right? And so the derivative, so basically what we're saying is that the slope of f of x equals e to the x at any point x comma e to the x, the slope is always equal to whatever the y coordinate is, right? So the slope is equal to whatever e to the x happens to be, and that's because f prime of x is itself e to the x. Okay, so it's kind of a remarkable thing about the exponential function, the natural exponential function. Good. So hopefully that was helpful. That proof. I know that can be a little sticky, but hopefully that was valuable. Let's take a look at some examples where we use this. So what about f of x equals 3e to the x? What's the derivative? Well, couldn't be easier. F prime of x is, again, you can bring the constant out front if you need to, but you know that that's just 3e to the x. Okay, so the constant doesn't impact it there. What about g of x equals x squared plus e to the x? Let's say that. G prime of x would be equal to d dx of x squared plus d dx of e to the x. And so we would know that that's 2x plus e to the x. Okay, no problem. And what about, how about something like this? H of x equals sine of x minus e to the x. And so again, h prime of x is d dx of sine x minus d dx of e to the x. And we can do this easily. Cos x minus e to the x. All right, so e to the x is a nice, if only the derivative were like that for everything. It's very easy to use. Okay, so let's talk about, let's kind of shift gears here ever so slightly and talk about some applications. Okay, so we've seen how the derivative can be used to determine the slope of a function, right? So that's sort of like its big use case. The derivative can also be used to determine the rate of change of one variable with respect to any other, right? So consider the position function. You may have heard of the position function. This is a function that's used in physics. So this function gives the position relative to the origin of an object as a function of time. Okay, so usually for a position function, people will frequently use s to denote the position function. The position of an object with respect to time. Okay, so I plug in a certain amount of time. If an object moves relative to time according to this position function, then this position function tells me where the object is after t time. Okay, so if over a period of time delta t the object changes its position by, so maybe we'll say delta s is equal to s times t plus delta t minus s of t. Okay, then we can use the formula, this formula. We can use the formula rate equals distance divided by time. Okay, and from this we would have the change in distance, change in position, change in distance divided by the change in time. Okay, so this is a derivative of the position function with respect to time. This is just a regular old derivative. So let's do an example using this and see, and then this will help us see how it is that differentiation is foundational to much of what we do in physics now. So let's take an example here. If a rock is dropped from a height of 100 feet, okay, its height s at time t is given by s of t equals negative 16t squared plus 100. Okay. So in this case, s is measured in feet and t is measured in seconds. Okay, so basically the idea is we start at 100 feet when t equals 0. The position is 100 feet. You can see how that would work. And then you drop the rock from height 100. It begins to pick up acceleration. It drops, rapidly towards the ground. And this function here tells us where it's at t seconds into its fall. Okay, so let's find the average velocity over a couple intervals here. Let's start with this. We'll start with one interval. Let's find the average velocity over the interval between 1 and 2 seconds. Okay, so we could just plug in here, right? So s of 1 second, let me just put the subscripts on there. That's going to be negative 16 times 1 squared plus 100. So the rock is now 84 feet off the ground. S of 2 seconds, okay, in that case it's going to be negative 16 times 2 squared plus 100, and you plug all that in, you get 36 feet. So these are feet. This tells you how high it is after 1 second, after 2 seconds. Now, 1 second and 2 seconds are rather far apart. Let's see what happens when we tighten up that interval. What about 1 and 1.5 seconds? Well, so again, s of 1 second is 84 feet. But what happens at s of 1.5 seconds? Well, it's just, again, negative 16 times 1.5 squared plus 100. Right? When you run those numbers, you get 64 feet. Okay, so you can see those are closer, okay, than those. What about just a fraction of a second later? Instead of 1.5 seconds, 1.1 second. Well, s of 1 second, just like before, is 84 feet. S of 1.1 second, okay, so we would have to plug this in, and we would say negative 16, and then it's 1.1 squared plus 100. And what would we get? We'd get 80.64, so you can see that we're getting really close. Okay. Okay, so now for each of these, we can calculate a delta S over delta T. Okay, so from 1 to 2 seconds, our delta S over delta T, right, would be equal to, if you recall, you have those written down, 36 minus 84 divided by 2 minus 1, right, and we get negative 48 feet per second. Okay, so the average velocity of the rock between 1 and 2 seconds is negative 48 feet per second. Now what happens at between 1 and 1.5 seconds? Well, there your delta S over your delta T would be, let's see, what do we write? 64 minus 84, and then it's 1.5 minus 1. And so here you would get negative 40 feet per second. Right, so that's the average velocity of the rock between 1 and 1.5 seconds. So it starts out slow, starts to speed up. On average, this is the velocity across that time interval. What about the really small fraction, 1.1 seconds? Between 1 and 1.1, so only 1/10 of a second. What does the delta look like there? Well, it's 80.64 minus 84 divided by 1.1 minus 1. And when you do this, you get negative 33.6 feet per second. Okay, so over that really tiny interval, the average velocity was negative 33.6 feet per second. Now notice that the average velocities are negative, right? Now that's important to know, because the object is starting up high and it's falling towards the Earth, right? So this is just choice of coordinate system, right? Okay. So what if, so this gives you this tells you the average velocity over an interval, but what if we want to know the instantaneous velocity of the object when t equals equal to 1, right? So you can see this These bounds are kind of shrinking up, closing in on 1. What about the actual instantaneous velocity at t equals 1 second? What about the, and here I'm going to put this in quotes, the instantaneous velocity at t equals 1 second? Can we figure this out? Well, this sounds like the derivative, right? So as we shrink the interval down to 0, we want to know what the slope of the line is at the 1 point, right? And here what we're saying is the 2 points of interest are 2 adjacent measurements of time. What if we continuously shrink this interval down until it's arbitrarily small, i.e. equal to just one instantaneous moment in time? Can we calculate the velocity? So again, letting st be the position function, we can calculate a velocity function like this. This is going to be the limit as delta t goes to 0 of the position function, which is just t plus delta t, minus s of t all over delta t. Right, now hopefully this is intuitive, right? That's what we're doing up here. We're taking our s plus delta t minus our s of t, right? And dividing it down by delta t here. That's what we're doing in this limit. The difference is we are kind of do this more like symbolically, and we'll see how what this shakes out. So this is obviously a derivative function. This is the definition. And so the derivative of the position function gives you the velocity function. Okay, and so what was our specific function? Our specific, our st was equal to negative 16 t squared plus 100. So we could calculate the derivative using this expression, or we can recognize that this function has nice structure that we can use many of our differentiation rules on. So that means s prime of t, which we just said was equal to velocity, is equal to negative 32 t, right, plus the derivative of 100 is 0, right? So that's where we can get to a function that tells us the velocity at any time t, right? So starting with a position function, we can derive a velocity function as the first derivative of position. Okay. All right, very good. So this is a super valuable physics. This is a super valuable application of derivatives in physics. In fact, if you take physics, if you take like an introductory physics course, this is almost certainly what you'll end up starting on. You'll start with this. If it's calculus-based physics, you'll start with this relationship. And what you find out is that, in fact, there is a chain of derivatives that you can use to differentiate position down into a whole bunch of things. So if you start with s of t, then v of t is equal to s prime of t. So the derivative of position is velocity. And then what you'll find is that something called the acceleration, a of t, is equal to the derivative of velocity, right? And so hopefully this is intuitive, right? The velocity is just the change in position with respect to time, right? That makes sense. The difference between my starting point and my ending point relative to time tells you how fast I got there, right? It's also the coordinates of like where I got to is important in velocity. The acceleration tells you, that's just I start out at a certain velocity and my velocity changes into something else, i.e. I accelerate, right? So this is hopefully this is intuitive. And then of course you can differentiate acceleration and get into other things as well, right? And it kind of keeps going for a little while. Let's do an example. Let's say let s of t equal negative 16t squared plus 16t plus 32. Let's let that be the position function for a driver. for a driver that jumps from a diving platform. Oh, sorry, not driver, diver. That jumps from a diving platform 32 feet above the water. All right, so you're up on top of this diving platform. Okay, and you got the water line down here, and this is 32 feet. All right. So when does the diver hit the water? Two questions. When does the diver hit the water? So at what time t? And what is the diver's velocity at impact? All right, so I jump off of this diving platform and I do this dive towards the water. First question, when do I hit the water? How long does it take me? Given this position function, I should be able to figure that out. And second question is, well, when I do hit the water, whatever time that happens to be, what's my velocity? Okay, so let's start with A here. Naturally, to identify the time when the diver hits the water, we basically have to solve this equation, right? Right, we need to know when the position of the diver is 0, right? So the position is the diver's position off the top of the water. So he starts up at 32 feet, and we need to know when his position is 0. So that's essentially just solving this expression, isn't it? Right, so we need to solve negative 16t squared plus 16t plus 32 equals 0. Solve this for t. Now this is a quadratic, so you're going to end up with two solutions. So let's see what we see here. We can factor out the 16. All right, so if I factor a negative 16 out, I get t squared minus t minus 32 is 0. And a little bit of work off to the side, you'll be able to see that t squared minus t minus 32 can be factored into t plus 1. Oh, I'm sorry, this should be a 2, minus 2, okay, not 32. So you can factor this into t plus 1 and t minus 2. Okay, so what does that mean? Well, the negative 16 is inconsequential. Right, so you have that. So that means we've got two solutions here, right? So the two solutions are t equals negative 1 second or 2 seconds. So obviously t equals 2 seconds is the solution that's relevant to the physical scenario, right? You can't have a t equals negative 1 second. Okay, so the diver hits the water after 2 seconds, given this position function. Okay, now the question is, what's this diver's velocity when he hits the water? So how do we know that? Well, we're going to need the velocity function, aren't we? So we know that the velocity function is the derivative of the position function. So it's going to be equal to d dt of whatever s is, right? So we can plug in negative 16t squared plus 16t plus 32. It's a simple polynomial, no problem. And for the velocity function, we'll end up with, and again, we can break this all apart using all the rules and everything. Maybe I'll do that just to be careful, just to make sure that people can see. That's sort of the point of the section. Negative 16 ddt of t squared plus 16 ddt of t plus ddt of 32. Okay, and so here you would get negative 32t and then plus 16, right? And then this constant goes away, goes to 0. The derivative of a constant is 0 is what I mean to say there. So this is the velocity function. So this tells us the velocity of the diver at any time t. And we can use this to figure out what the diver's velocity must have been when he hit the water at 2 seconds, right? So all we got to do is plug in v of 2 seconds, right? Then I get negative 32 times 2 plus 16. And if you do that math, you get negative 64 plus 16, and you'll see that it's negative 48 feet per second. Okay, so the diver hits the water 2 seconds after the dive starts, and at that time, when he hits the water, his velocity is equal to negative 48 feet per second. Really booking. Okay, so that's just the force of gravity acting on this person. So, all right. Now there's a lot more examples, of course, that we can do in the realm of physics, and we will get into a lot of those a little later. But for now, I think we'll end Lecture 7 on that note.